All right. Hello, everyone. So I wanted to have a short video recorded here to provide a little bit of clarification on this first homework assignment. And so first of all, I wanted to talk very briefly about skewness and kurtosis. And so previously we had introduced some equations that could be used to calculate and assess the degree of skewness and kurtosis. And so again, when we talk about skewness, we're referring to the third moment about the mean. So basically we're taking each observation, subtracting off the mean, and then cubing that quantity. And that's giving us a sense of how symmetric these distributions are. And so the formula to estimate that parameter is as shown right here for gamma 1. So we would subtract off that population mean, which is known to us, cube that for each data point, and then sum that and divide by basically the third power function, so the standard deviation to the the variance to the 3/2, or the standard deviation cubed. Now, in practice, we don't have those quantities available to us because typically the variance is unknown and the mean is unknown, and we're estimating that based on sample data. And so previously, we had presented the equation for lowercase g1 that you see indicated here, where we're basically taking each observation, subtracting off the sample mean, and then either cubing or squaring that quantity respectively. And then you'll notice here we're dividing by n instead of n minus 1. And so this is how we would estimate the skewness if we were able to observe the entire population. Now, in this case, we're generally only observing a sample. And so there's actually a minor adjustment factor that's introduced, as you see down here. So it's similar to how we would adjust the sample variance and subtract off n minus 1 rather than dividing by n directly. And so in this case, it's a little bit more complicated, but it's a straightforward application. You're just going to take the square root of n times n minus 1 all over the quantity n minus 2. And then multiply by the estimate we have for G1 as shown here, okay? And so the same protocol as before apply. You know, we want to stay within that plus or minus 1/2 to discern that the data are essentially symmetrical. And then if we get beyond that, up to plus or minus 1 would be moderately skewed, and anything beyond that skew would become a particular concern, okay? Likewise, in the case of kurtosis, we're basically measuring how frequently extreme positive or negative values are occurring out in the tails of these respective distributions. And so that quantity is calculated as shown for gamma 2 right here. And likewise, we can estimate gamma 2 using sample data as shown for the calculations here for G2, where we're taking either the fourth moment or the second moment about the mean for these respective data points. And the correction here is a little bit more involved, but in essence, we're just using this formula that you see right here in order to make these adjustments. And so the upshot of this essentially, and again, keeping in mind here, we're going to subtract off 3 if we want to talk about excess kurtosis, where this would basically be normalized about 0 instead of about 3. And the reason I'm introducing these sample formulas is in part because this is how Excel and various other software programs are going to calculate these same quantities. And so just to make this clear to everyone, I'm going to go through a very brief demonstration of these respective properties and their calculations in Excel, okay? Okay, and so here we are in Excel, and what you see here are basically some of the data that were used as a part of our lecture that focused on dependent or paired sample t-tests. And so this is basically just showing the 10 observations that corresponded to variable x sub 1, which was the number of crashes that were experienced prior to the signal timing changes at each of those individual locations, okay? Now, I'm going to make this a little larger for everybody's convenience here. Now, what I've done down at the bottom is I've taken the average of those quantities. And so as you recall from the lecture, that average was 9.2. And then I have a series of intermediate calculations here where I've taken the second, third, and fourth moments of each observation about the mean. And so all I'm doing here is taking each individual x sub I, subtracting off the mean, and raising that to either the second, third, or fourth power as we look at columns D, F, and H here respectively. Okay. And so if we sum those respective quantities, we see those are all indicated right here. And then we simply divide by the sample size to arrive at our estimates M2, M3, and M4. And these would correspond to the exact same calculations we see in the sample slides. And so if we apply those formula directly to get the lowercase g1, as you see here, you'll notice in this case, we're taking M3 and we're dividing by M2 to the 1.5 or 3/2 power. And so that makes that quantity unitless. And so this would be our skewness if we were measuring the entire population. Now, since we're not measuring the entire population, if we look at this formula here, you'll notice there are some adjustment factors that are introduced. And so that's where we basically add this final term here, where we're taking the square root of n times n minus 1 and that entire quantity divided by n minus 2. Okay, so we're just manually entering those calculations that were demonstrated on the preceding slides. Likewise, in the case of G2, in this case, we're just taking our quantity M4, and then we're dividing by M2 quantity squared. Again, that would make that quantity such that it's unitless. And we're subtracting off 3, so this would be reporting our excess kurtosis rather than our kurtosis. Okay, so just to clarify that point. And then we introduce the same correction that was illustrated in those slides respectively. And so we're taking that quantity and we're then introducing the same adjustment factors that were demonstrated on the preceding slide. And that would include, in this case, a quantity n plus 1, and we're adding a 6. And then we've got n minus 1 all over the quantity n minus 2 times n minus 3. And so that gives us the sample estimates for those skewness and kurtosis parameters. Now, as a quick check of our work, Excel actually has some built-in functions. And so this is real simple and easy. All we need to do is type in equal skew, highlight our respective data set, and you'll notice that will report back that same estimate of sample skewness as we had just calculated manually. And likewise for the kurtosis parameter, we're just going to use equal kurt and then highlight those same columns, those same cells, and that will give us an estimate of the sample kurtosis. Okay. Okay, so I also wanted to demonstrate in Excel how we can quickly check our work when we're trying to conduct t-tests. And so this is the same data set we worked through as a part of our lecture on dependent or paired sample t-tests. And so you'll notice here, I've got our mean values, our variances, and our standard deviations calculated manually, but we can actually do all of this work using the data analysis tool pack in Excel. And so you'll want to verify that this application is installed. It's not installed by default. And so there is an analysis tools option, and you just want to make sure that analysis tool pack is checked. If it's not, checking that will then result in that application being added to your toolbar, as we see right here. Now the interface will look slightly different between PC and Mac environment, but ultimately we'll want to click on where it says data analysis here. And you'll notice there are a whole bunch of different types of operations and statistical tests and analyses that we can conduct simply using Excel, okay? And the 3 that we're particularly interested in here are the t-test for paired samples, and then the t-test assuming equal variances, which would be students, and unequal variances, which would be Welch's, okay? And so we'll start with the test that we had initially started with, students T. And so I'm just going to click on t-test for 2 samples, assuming equal variances. You'll notice here it's going to ask for me to highlight ranges 1 and 2. And so I'm going to highlight my first sample of data and run that all the way up so that it also includes the data labels. I'll explain why in a moment. And then likewise for the second array, I'm going to take the second column running all the way up to the header row. You can specify a hypothesized mean difference we're interested in comparing against. By default, that's just going to be equal to 0, which is our most common application in practice. So we're just testing whether or not there's a difference of any type. I'm clicking labels here, and that's just going to tell the program, the application, that that first row in that data set is comprised of labels rather than raw data. We can also change our associated significance level here. And then as a last step, our output can either go into a brand new worksheet, or we can specify where we'd like that included on our existing sheet. And so I'm going to use that latter option here. So if I just click in cell E1, that is where the output from this function is going to be reported. And so I hit OK. And what you'll notice here, I will just increase the size here real quick. These numbers should look very familiar with what we worked through in class today. So our mean number of crashes in the two data sets are 9.2 and 7.4 respectively. You see the associated variances and sample sizes, as well as our estimate of the pooled variance. Our degrees of freedom, which in this case is just going to be N1 plus N2 minus 2. And then you'll see the calculated t-statistic of 1.69, as well as the associated p-values and the corresponding critical statistics so that we can assess those appropriately. And consistent with what we had seen earlier today, in the case of a one-sided test, we didn't quite have enough evidence to reject, so we weren't able to meet that 1.734 critical value. And so our p-value is just above that 0.05 threshold, okay? Now we can use the same functionality here, and rather than doing students test, we can apply Welch's, which is just the t-test for two samples, assuming unequal variance. And so we're going to highlight the exact same information as we had in the preceding example. I'm going to leave this blank as it's not a necessary condition. I'm going to indicate that we have labels. And in this case, I'm going to select a different output range. You just want to be somewhat careful you're not copying over old data. So I'm going to select I1 as the starting point for this output. And then we hit OK. And again, as we had noted previously, our hypothesized difference here, let me just expand these columns real quick, by default is set to 0. You'll notice in this case, we don't have a line per pooled variance because we're not concerned with the pooled variance in the case of Welch's test. Our calculated test statistic is the same as we've seen previously. You'll notice the marginal increase in our critical value for T, and again, we fail to reject the null hypothesis in this instance. Okay. And lastly, we'll run through that exact same exercise a third time, this time using the paired sample t-test. And so the setup here is the exact same. We're highlighting sample 1 and highlighting sample 2. We've included labels, and we're going to output this information right here, starting at M1. And there we have it, the same calculations we had worked through this morning. You'll notice in addition to the other information, it's also providing an estimate of the Pearson correlation coefficient. So we haven't talked about this yet, but this is just basically measuring how strongly correlated X1 and X2 are to one another. And so the higher this value is, the more advantageous a paired t-test would be as compared to the independent sample t-tests. And that's reflected by that larger t-statistic as we had saw this morning, so 3.67. And you'll notice that's going to be highly significant. The p-value in this case is less than 0.002, so it's well below our 0.05 threshold, okay? And so what you can do in short here is basically check all the work that you're conducting as a part of the first assignment. I do ask that you provide at least some manual sample calculations or intermediate steps just to understand that you're familiar and understanding the concepts that we're working through. But moving forward, you can feel free to use Excel or the other software tools we'll be introducing. So hopefully this was helpful for you all, and I will be in touch soon. Thank you very much.